Okay, Jeff, I think we might as well get started. And
Super.
we're up to 38 participants, so that's great.
Yeah, no, that's great. That's really good. Okay, so there may be some participants joining us this evening from other RASC chapters, and also there may be some students from the astronomy faculty at the University of Victoria. I'd like to welcome everyone to this meeting of the Victoria chapter of the Royal Astronomical Society of Canada. My name is Jeff Pivnick, and I'll be coordinating the presentation this evening. Chris Pearce, who is our usual host, will be doing the IT backup in the absence of our usual IT guru, Joe Carr. As a group, the Victoria chapter usually meets weekly for sessions called Astronomy Cafe. Every month or so, we try to have an invited speaker as we do this evening. For the local members, we'll continue with the regular chapter meeting activities after this presentation. The guests are welcome to stay for the meeting or log off as they wish. Or just a little bit of housekeeping. During the presentation, please mute your audio. It makes it much easier to hear the presentation without any other interference. We'll have a Q&A after the presentation. For that, please use the raised hand function. Chris and I will monitor the hands and I'll call the questions in order. Remember, though, to unmute your speaker when you're asking a question, and then please lower your hand after the question's asked. So for the presentation. On September the 26th, we were able to witness the DART spacecraft impact on the small asteroid Dimorphos. The dual asteroid redirection test was a test of concept for NASA's Planetary Defense Coordination Office, coordinating with NASA's Near-Earth Object Observation Program. As its name suggests, the Near-Earth Observation Program is tasked with identifying, locating, and tracking near-Earth objects. Dr. Kelly Fast manages that program, and she'll be speaking with us this evening. So for a very brief background, it's going to miss a number of her accomplishments. Dr. Fast is an astronomer who has worked in planetary sciences, focusing on primarily planetary atmospheres through most of her research career. Following her thesis work, she took a job with NASA, first at the Goddard Space Flight Center and later at NASA's headquarters. Her numerous projects with NASA have included studies of solar, Jovian moon, and Martian atmospheres. Due to the extent and excellence of that work, she is among those individuals who has had a main belt asteroid named after her. Asteroid 115434 is now named Kelly Fast. I'm pleased on all of our behalf to welcome Dr. Fast to speak with us this evening. So Kelly, you can take over with your screen.
All right, thank you so much, Jeff and Chris, and thank you for the kind invitation, and I'm very pleased to speak with you this evening. Yeah, I started in astronomical research, and my first observing run ever was Comet Shoemaker-Levy 9 impacts with Jupiter in 1994, and back then I was studying what it did to Jupiter's atmosphere, and I didn't know over the years my career would kind of take it around full circle, as I say, to now studying the impactors, or really enabling the study of the impactors, working now more in on the management side of things at NASA headquarters. So let me, oops, just a second. I realized as we were testing the screen, I need to reset my presentation here. Okay, here we go. Let's see if this is displaying properly. All right, I think we're good to go. So, so in my role in the Planetary Defense Coordination Office at NASA headquarters, I manage the Near-Earth Object Observations Program, which involves finding the asteroids, like what Don Yeomans in our community has said in the past. And then sometimes I like to add getting the asteroids. And so you're going to hear also about the DART mission tonight. What I'd like to do is give you an overview of what happens in planetary defense at NASA, and then also giving some highlights from the DART mission, which you are probably familiar with just because it got a lot of attention, and we were very pleased with how things turned out. But I'm going to go through and try to give you an overview of the program, and then we'll take some questions. but this is kind of a funny joke to start with. This is a picture of an asteroid crater in Arizona. Look how close it came to hitting the visitor center. But asteroids have impacted Earth and other solar system bodies throughout the history of the solar system. And so it happens, certainly it was much more frequent early in the history of the solar system. It's a very infrequent event. This impact here was probably 50,000 years ago. So something of substantial size doesn't impact very often. We get impacted all the time by material, and you see shooting stars and maybe a fireball. It's a lot more rare that an object of significant size that could do damage to the surface of the Earth actually hits us. Might not ever happen in our lifetime or our children's lifetime, but we have the capability to look and prepare. And so that's part of NASA's program and other astronomers around the world working on this, because we have the capability. And so we should do what we can to be ready, even for a rare event. And so probably don't have to give much background to this group, but just from the International Astronomical Union definitions, an asteroid is an object in space, a natural object in space larger than a meter in size. That is a comet, and a meteoroid is smaller than a meteor in size. So just those definitions. And then the meteor is that visible phenomenon in the atmosphere when a piece of material enters the atmosphere and disintegrates on the way down. And then sometimes some of those pieces survive and reach the ground. And so those are meteorites. So just going through our terminology. And then the definition of a near-Earth asteroid, because we've got the asteroids out in the main belt between Mars and Jupiter. But the near-Earth asteroids are the asteroids and comets with orbits that bring them within about 1 1/3 times the distance from the sun to the Earth. Or with this group, you know what an astronomical unit is. So essentially in that blue zone, and some of those asteroid orbits might be almost within that area. Some of them, they're coming in from the main belt because they've been tweaked by Jupiter's orbit and venture into the inner solar system. They're all different kinds of orbits, but what they all have in common is bringing them to this part of the solar system. But there are many objects that are near-Earth objects that never actually come close to Earth's orbit or to Earth. And so the subset that we're really want to focus on is the potentially hazardous objects. So the NEOs with orbits that bring them within 7.5 million kilometers of Earth's orbit in that red zone there in the plot, and of a size that can do regional damage should they impact Earth, which we use as 140 meters in size and larger. You'll hear that number used later. So those are the objects we really want to keep an eye on. I mean, the much larger objects, what in the news they might call the dinosaur killers, there's fewer of that population. They're much larger, and easier to find, not finding very many of them every year. So it's not that population we're concerned about so much, or the smaller population that, again, Earth's atmosphere takes care of, but kind of this in-between size that we know we're still finding them, and we want to keep finding them, get them cataloged, know where they're going to be in the future, so we know if an asteroid and Earth are going to ever be at the same place at the same time. And just for context, you've probably heard of NASA's OSIRIS-REx mission, which has visited the asteroid Bennu, and it was a sample return mission. It's collected a sample that's going to drop off back at Earth, studying Bennu, but it's actually one of the most potentially hazardous asteroids, and yet still there's nothing on the risk list that is even up at the level to be concerned, just more keeping an eye on it, but gives you context about where Bennu's orbit is. You know, these asteroids that come close to Earth's orbit, we want to keep particular eye on. But really, it's the ones we don't know about which we're concerned. So NASA's been doing this kind of work since the late 90s, but this really got formalized in 2016 with the establishment of the Planetary Defense Coordination Office, taking its legacy Near-Earth Object Observations program and then folding in the other activities related to planetary defense, involving like coordinating with other US agencies, with our international colleagues, you know, to study and plan the response to the asteroid impact hazard. And so the Planetary Defense Coordination Office at NASA is tasked with detecting any potential for significant impact of planet Earth by natural objects, praising the range of potential effects by any possible impact, and then develop strategies to mitigate impact effects on human welfare. And just a visual way to look at all of that. One of the key areas, again, is finding asteroids and comets. If you don't know that they're there, you can't do anything about them. So that's kind of the bread and butter of the program, searching for asteroids, detecting and tracking them, calculating their orbits. Also characterizing them, understanding their properties. Are they rocky objects? Are they more metallic? Each asteroid, just like our children, are individuals, and trying to understand those objects. Planning and coordinating, I'm going to mention later, we have some international groups, collaborations. I had mentioned before the meeting, we were talking about the International Asteroid Warning Network. Those meetings happen to be going on this week, and so working with our international colleagues and with our colleagues in other US government agencies to address the hazard. Mitigation, doing something about an impact, and DART falls squarely into that, as you'll hear about a little later on. And then assessing where we're at. Where are we at in terms of addressing the near-Earth asteroid hazard, and what can we do about it? So again, the primary goal, kind of goal before all else, is finding near-Earth asteroids. And it is like finding that needle in a haystack, because, as many of you know, if you're astronomers and looking at the sky, asteroids and then other things moving in space, they're just moving points of light in front of other points of light, the stars. And so that what makes them stand out is seeing that motion. And so you can see there in that GIF from the Catalina Sky Survey, circled in purple, there's a near-Earth asteroid moving across the field of view there. And so we have telescopes that with wide fields of view, looking at large swaths of the sky and watching for those moving objects and observing in such a way to be able to catch them at different times, so that you can get enough information, enough positions to figure out where they've been and where they're going, to calculate an orbit. Forgive me just a second. I'm getting the meatball of death here. Oh, there we go. Okay. All right. It paused. The government's probably forcing a software update to me right now. So hopefully not right now, please. Some of the assets that are doing the search part of the program funded by NASA, the primary assets are telescopes of the Catalina Sky Survey, the University of Arizona, in the state of Arizona, and also the Pan-STARRS observatories in Hawaii, at the University of Hawaii, on Haleakala on Maui. These two survey telescope systems are providing the bulk of the discoveries worldwide for near-Earth asteroids. Most of the discoveries are coming from NASA-funded telescopes, but then telescopes around the world are helping with the follow-up and providing additional information. But these two projects are providing the bulk of the discoveries. There's also the Atlas telescopes, which are smaller robotic telescopes that don't look as faint as these other telescopes, but they cover the sky more quickly and are a good complement, maybe catching something that might be falling through the cracks. There are two telescopes in Hawaii, on Haleakala and on Mauna Loa. And then just this past year, two additional telescopes were built with NASA funding to University of Hawaii, and then with their collaborators in both South Africa and in Chile. And we'll see some images from one of those telescopes later related to DART, but getting some good southern sky coverage. Also, for good coverage of the southern sky, the Space Surveillance Telescope, which was in New Mexico and was moved to Australia as a joint project of the U.S. Space Force and the Royal Australian Air Force, doing its space surveillance of objects in Earth's orbit, but it also picks up asteroids. And so we fund the Linear project at MIT Lincoln Labs to pull the natural object data out of the data from this telescope. And we're still getting things in place now that they've gone operational in Australia to get that pipeline going again. We also fund the data processing on the Caltech's Zwicky Transient facility in California. And finally, NEOWISE, we actually have a space telescope, but it's a repurposed space telescope. This was the Wide Infrared Survey Explorer mission, which was an astrophysics mission. It was doing a survey of sources outside the solar system, but asteroids are going to photobomb anything, and that was realized. And so a pipeline was put together to actually pull those data out of NEOWISE. And once that mission completed and its cryogenic channels had run out of cryogen, it was later reactivated using the remaining non-cryogenic infrared channels to continue its survey. And it's really doing more to provide size information on asteroids, because it can do that in the infrared, but also finding some asteroids and really being a good pathfinder to how would we do this in a more targeted way from space, which we'll talk about later. But here's where these telescopes are around the world that I just mentioned, in Hawaii and the southwest of the United States, but then also with some of these sites in Chile, South Africa, and then get up and running in Australia, and also NEOWISE in orbit. But there are lots of, there's lots of telescopes used to follow up these discoveries, to get additional observations, to have enough to be able to calculate an orbit. It doesn't help to see an asteroid if you can't find it again in the future, if you don't know where it's going to be. And so these follow-up telescopes are very important. These are the ones funded by NASA, but there are also telescopes that are operated by in other countries that contribute to these efforts. So again, planetary defense is a worldwide effort. There we go. All right, so all of those observatories that are looking at position measurements of asteroids and of comets, of any small bodies in the solar system, they submit their observations to the Minor Planet Center, which is actually funded by NASA as part of its Planetary Data System Small Bodies node now. But it has been, and still is, the internationally recognized repository for small body measurements, recognized by the International Astronomical Union. And so they are responsible for the identification of these objects. Is it a natural object? Is this a new object? Giving it a designation, doing an initial orbit computation. But then, let's see, I'm gonna hide the videos here. Sorry about that. I'm trying to find the room on my screen here to find everything. But then the Center for Near Earth Object Studies at the Jet Propulsion Laboratory in California, they pull the position data, and they do the really high precision orbit determination for these objects, both in the short term with new discoveries, even before they've been confirmed, just to see, is something that was just picked up, does that pose an immediate impact threat? But then also looking in the long term, could anything pose a threat into the next 100 years, doing that orbit determination way out into the future. And in the event that there is a predicted impact, that they would determine the time, location, and geometry in the event of such an impact. Now, as I was mentioning earlier, I mentioned the International Asteroid Warning Network. That's one of two collaborations that were international collaborations that were recommended by the United Nations and have been meeting for a number of years now, since 2013, both building these collaborations and then reporting out to the UN. It's the International Asteroid Warning Network is one of them, which is the collaboration of observers, orbit analysts, modelers, who are out there finding the asteroids, trying to determine if any pose a threat, and would report on that in the event something does pose a threat. And it's organized by NASA right now. And its companion group or counterpart is the Space Missions Planning Advisory Group, which is a collaboration of the space-capable nations, their space agencies, to look at potential mission plans, to be able to recommend possible plans in the event to their governments in the event that there's an object discovered that's an impact threat. And then again, this would ultimately we expect to be a collaboration, because it's going to take more than any one country should there be a situation that's discovered like this. And so having these collaborations working together now is very valuable. We sort of had an exercise of our systems just earlier this year, in March of this year, there was a small asteroid that was first observed and almost entirely observed by an observatory in Hungary. Reported the observations to the Minor Planet Center, and the Center for Near Earth Object Studies, or CNEOs, pulled those observations and calculated that there was going to be an impact. The first observations were made about 2 hours before impact, and about an hour before impact, there were enough observations that had been reported to the Minor Planet Center. It was enough to calculate enough of an orbit to determine that this object was going to hit the Earth. Now, it was a very small object. You could tell from the brightness that it was very small, a couple meters in size, nothing that required warning. The atmosphere would take care of it, but it was a good opportunity, again, to kind of go through the motions of calculating where it was going to hit. This is only like I think this is like the 5th time that an object had been discovered in space before impacting the Earth. So, and it was very small. That's why this was so last minute. If it was a larger object, this would have, would have been spotted further out if it had been in the nighttime sky. And again, the goal is to spot them years or decades in advance. But in this situation, here, kind of in a short warning, about an hour before impact, this is where the impact location was calculated over Greenland and northeast of Iceland and over the Norwegian Sea. And so as additional observations came in, the uncertainties went down and that impact location narrowed until finally about 20 minutes before impact, it was zeroed in on northeast of Iceland. And so this is where CNEOs calculated that the impact would take place, and our counterparts at the European Space Agency went through a similar process and calculated this. And even though this was over water, so there was no one there to see it or collect meteorites or anything like that, it was still detected. US government sensors detected the energy release from the fireball, and these observations actually are shared and publicly released on the CNEO's website. And that particular object was measured, and it was also, this impact was also detected by Comprehensive Testband Treaty Organization infrasound sensors, really low frequency sound waves. So it was just really good confirmation that the orbit determination and the impact corridor calculations, that's something that we can trust in, that getting good confirmation of that with the data that it's able to use. So that was really encouraging. And also this year, over the years, NASA and FEMA have done some tabletop exercises looking at hypothetical impact scenarios and working through, just so there's an understanding, even though FEMA, other agencies have plenty to deal with hurricanes and tornadoes and earthquakes and pandemics, but still, this is the sort of thing that you don't want the discovery of a threat to be the first time that anybody has ever thought about it. And so these exercises have happened over the years. And then this year, there was a 4th exercise that this time involved a wide range of agencies in the US government, and just getting together with representatives and sitting down and working through an asteroid impact scenario. In this case, it was a warning time of 6 months, and talked through the situations. It was something where it was designed to be something where you couldn't send a spacecraft, and so it allowed the emergency management agencies on the federal and state and local level to kind of look at, how would they handle such a situation, because they're the ones with the tools for doing such things, and how would NASA be informing, what roles would other agencies play, and in this case, the state of North Carolina took the hit. But all of this is kind of exercising out what was released in 2018, a national near-Earth object preparedness strategy and action plan from the US government, really just a high-level plan for what do we want the different agencies working toward in the next 10 years in order to be better prepared for an asteroid impact. And so that's ongoing. We're about halfway through that action plan and are looking at how to see where we need to be by the end of that 10-year period. And so where do we stand in the search for near-Earth objects? And all this information is on the Center for Near-Earth Objects Studies website. But we're actually over 30,000 known near-Earth asteroids. And over 10,000 of those are over 140 meters in size. And we say that because that's our, in the US, it's actually a tasking from the US Congress to NASA to find the objects of that size range. I mean, we want to find and catalog any of them. But again, this kind of intermediate size range are the ones where we're still finding a lot of them. It's thought that over here that from modeling, it's estimated there's about 25,000 of that population. And we're only about 41% of the way there. And with the assets that we have right now, it's going to take more than 30 years to really fill in that pie chart and get these more hazardous asteroids cataloged. But again, we're looking at how to speed that up. Again, NASA started doing this back in the late 90s, and this is what we refer to as the George E. Brown NEO survey goal, this tasking from Congress to do this. And so here's part of how to speed this up, what NASA is working on. The area at opposition, as you all know, that's what's seen by ground-based telescopes nighttime. This direction is night. And I mentioned the NEOWISE mission, which is in this sun-synchronous orbit around the Earth. And so it's kind of looking in this narrow range as it orbits the Earth, and then that'll sweep out the sky in 6 months, but it's not being done in a targeted way, looking for near-Earth asteroids. And so NASA's developing the Near-Earth Object Surveyor Space Telescope, which is a space-based infrared telescope to accelerate the survey to find the potentially hazardous asteroids, to get to that 90% in 10 years, and to get object sizes, which is really important. It's something that you can do much better in the infrared than you can do in the optical to constrain the sizes. And this red cone shows its field of regard, where it would look in swaths of the sky within these red cones, each direction, looking along Earth's orbit. So really targeting asteroids that come close to Earth's orbit, and also being able to look closer to the direction of the sun, which is helpful, very complementary to the nighttime observations from ground-based telescopes, and to be able to see more of the sky as asteroids come into those regions, and in particular the asteroids that are most hazardous to Earth. And what was really good was that the preliminary design review for this project happened just last month, and the project passed that. And so we're moving forward. And this is why infrared is important. If you have asteroids in space, you might not know their coloring or their albedo. And so same size asteroids, you put them way out in space, reflected sunlight, it's hard to infer the sizes from those differences. But if you could turn on your infrared eyes, looking at the heat that is re-radiated from these asteroids, then that kind of makes the size pops out. And so you see that much darker asteroid there. It's a lot harder for it to hide. And so this will help to accelerate finding some of this darker population, but also just getting better size information in general for anything that's detected. Whereas in the optical, you have more of a factor of 2 uncertainty or 3 in trying to determine the size just from the optical, the visible light. So the infrared will be really valuable. Just really quickly on characterizing NEOs, you also want to get to know that needle in the haystack, what its properties are if it were to impact Earth, if it posed a threat. How big is it? What is it made of? Is it rocky, or does it have a lot of metallic content? Is it solid, or is it a rubble pile? Is it what's its shape? How fast does it spin? Is it a single asteroid? And some of the assets that NASA has to do this sort of work for physical characterization. NASA's Infrared Telescope Facility out on Mauna Kea in Hawaii does infrared spectroscopy to look at the spectral properties of asteroids and be able to infer some information on properties and composition. And then also the planetary radar at Goldstone. You can't search for asteroids with radar. It's not powerful enough, and you just don't have the power to go sweeping out into space to search for asteroids. But if you know where they are, if you have accurate information from the ground-based optical telescopes, then you can bounce radar off of asteroids, and you can get some really good information. You can really nail down the orbit even better. You can get information on spin, but boy, if they pass close enough that you can do radar imaging, this is a little different than the actual image of an asteroid, but you can get so much information on shape, on the size. Is it a bilobed object there, like a JO25? Does it have craters? Does it have moons? Does it have multiple moons? So ground-based or rather planetary radar is the most powerful technique for studying asteroid properties, other than sending out a spacecraft mission. But you have to, they have to pass close enough to be able to bounce radar off of them. Okay, so we're getting to DART because I know it's what everybody's probably excited about, but just real quick, what are some of the other, as we talk about mitigation techniques, what are some of the techniques for deflecting an asteroid now that we know how to find them and track them? So one of them is the gravity tractor, which is just really taking, as our planetary defense officer says, using nature's tug rope, gravity, just putting a mass next to an asteroid, a spacecraft, or the idea of an enhanced gravity tractor would be to have a spacecraft that goes and maybe plucks a boulder off the surface to give it even more mass and then just hover there. If you had a long lead time, it's a very controlled way to deflect an asteroid and be able to move away or to move back in, depending on what needs to be done. So just need long lead time for this, but that's a technique. Now, as we call the Hollywood option, using a nuclear explosive device, it's always blowing it up in the movies, and that's not necessarily what would be done, because there are folks at U.S. national labs and elsewhere that study this sort of thing, how you would use it, because you can only, of course, do this as a study at the moment, but how would you do that? How would you use it to deflect an asteroid? And really, you would detonate next to an asteroid, and that would irradiate the surface, and that surface shell would blow off the asteroid, and so you would get that reaction force in the other direction, providing that deflection. So that's that technique. But what we really want to hear about is DART, and I'm sure you've seen the news. DART was launched last November, and then on September 26th, impacted the moon of an asteroid, the asteroid Didymos, and it impacted the moon Dimorphos. And this was really useful because this was a way to provide a change in the trajectory of an asteroid and do it in a way that's measurable by doing this binary asteroid study. And so DART impacted an asteroid and slowed it slightly to drop it into a little different orbit around Didymos. And that change could be observed from Earth, as I'll show later. And so it was a way to do kind of an economical mission where you had this ground-based astronomy component to it. And as you heard, it was quite a success. So so the goal was to target this binary asteroid system that was making this approach to Earth, where it could be observable from the Earth. This asteroid poses no threat to Earth and couldn't make it a threat even with DART. And so that's why it was a really good opportunity to use it as a laboratory to study the kinetic impactor technique, which is really the simplest of the asteroid deflection techniques, just impacting an asteroid to change its motion in space. And, physics and calculations, that's one thing, but to actually test it on a real asteroid with real properties and real shape and real spacecraft, this was a really valuable opportunity. And so DART was launched last November, and it had that impact on September 26th. It also carried an Italian CubeSat that was released in the weeks before DART impacted the asteroid, to be able to image that impact and any plume that might happen and send that information back. And then the rest of the observations took place from Earth, determining what the period change was. And as you might have heard with the news releases we had last week, it was a nice, decent period change of a half an hour of a 11, almost a 12-hour orbital period. So here's what DART was supposed to do. It was supposed to impact the asteroid. That was one of its requirements, of course, but it sounds pretty simple, but here you had a relatively small object and trying to hit it with another small object. Everything was going very fast. There was the Deep Impact mission a number of years ago, impacting comet, not to deflect it, but for science to release a plume of material. And that comet was a whole lot bigger. And so this was tough to be able to actually start from Earth and get all the way there and impact this asteroid. Change its period, the period of the orbit, measure that change using telescopes on the ground, and then also measure beta, which is kind of this enhancement factor from whatever plume material might be thrown off. Like if you were standing on a skateboard and you threw a baseball one direction, you would go sliding back the other direction. And so there's that enhancement that comes from real material being kicked off of an asteroid. And so this is an interesting mission where it involved the spacecraft, but actually the mission is still going on right now. There's just no spacecraft to continue it. And these were the charts from before impact. And so you can kind of see what the team was dealing with here, where it really wasn't until, the few minutes before impact that that the asteroid, the target asteroid, was going to be seen really well. And so, and because of the time delay with communicating to Earth, the spacecraft had to be able to have this autonomous navigation, and it worked very well. The team didn't even have to step in, but it needed to be able to line up on Didymos, and then as it got closer, to be able to offset to the smaller asteroid Dimorphos and to continue in. And the team didn't have to step in and say, you're going for the wrong asteroid. But again, it's just in the few minutes beforehand that those details were there. And then you've probably seen this. This is sped up, but here is the approach from the camera. I mean, very simple. This is a spacecraft with a camera, and it had one job: hit the asteroid. And so we were having a ball watching these images come down, and the scientists and us were starting to analyze what we were seeing about Didymos there, because we learned so much from radar. But then we're seeing the actual shape, and then here's Dimorphos coming in, and look at that, it's a rubble pile. And I'm thinking, oh my goodness, we're going to get a plume. Here are the images right before impact, the last views from DART, and then as you can see there, that last image. It kept sending down images until there was no more spacecraft, and so this was the very last image. So just a huge success. So let me get us to the next slide. And I mentioned that ground-based component. The big thing was measuring the change in the orbit, which I'll talk about, but also just a lot of observatories, both being part of this campaign and not, observing just the impact itself. It was visible really at the time of impact. It was over on this side of the world, Africa, Europe, and Indian Ocean. Really, it was kind of the hot spot there, and then later became visible from other parts of the world. But the observations of the impact, but also long term here, measuring what that period change was. And here's actually, I mentioned those Atlas telescopes that NASA paid to build in Chile and South Africa. This is from Atlas in South Africa at the time of the impact, seeing the Didymos system, and then this plume of material being released from the impact. I mean, there's still some speculation. This initial plume might have actually been some of the fuel from the spacecraft, but still just amazing. It was kind of better than our expectations. And again, these observations were coming in around the world from this one shows all of the continents practically contributing to observations of the impact, and ended up creating a plume, and almost a comet-like tail now is formed, or this is another, we've created an active asteroid. So a lot of good science to be done, as well as the targeted work for DART. The Hubble Space Telescope and James Webb Space Telescope also were part of this, getting observations of the plume after the impact. This is a little later on with Hubble Space Telescope for getting the details on this tail that has formed from the debris that was released by the DART impact. But this is really neat. This is from that CubeSat Lucia cube that was contributed by the Italian Space Agency as it flew by Dimorphos and Didymos. And so you can see the plume of material coming off of Dimorphos on the way in and on the way out, and also a chance to see, you know, more of the shape and surface properties of both Didymos and Dimorphos. And then they're still working on they're still bringing some of the images down, but they've gotten a lot of them down and working on all the contrast and the image processing. But just to have all of this is just absolutely amazing to see what it was captured there. Even though the period change is being measured from the ground, just to have, again, this information on what the plume was like is going to be really valuable for the team that is trying to model all of the physics of the dart impact and the deflection. Because again, this is something to kind of have this actual experiment in order to understand better how to, if we needed to do this for real one day, and how to scale it up. Oops. Now let me go back and forth. This animation always has trouble. One more time. Okay, come on. Let's try the other way. I apologize. I thought I had this working. Okay, there we go. All right, picture Dimorphos going around Didymos. Sorry about the trouble there. But as the one asteroid passes in front of and behind the other, the combined light from those two asteroids, it's going to go up and down as one asteroid is in front of or casting its shadow on one, going behind the other. And so that's called the light curve. And so you're going to see that, let's see if I can force this again. Oh, well. So even though from space, I mean, rather from the Earth, Dimorphos and Didymos just look like this single point of light. You see the light going up and down and up and down. And the team measured very carefully that up and down of the light curve before impact, so that they could really see the change in it after impact. And this is what was announced last week, kind of sooner than expected, but they were getting data sooner than expected at a level that they had the confidence in that they could go ahead and report. And so before DART impacted, it took Dimorphos almost 12 hours to orbit the larger parent asteroid Didymos, 11 hours and 55 minutes. And since DART impacted Dimorphos, astronomers have been using telescopes on the Earth to measure that, and the investigation team confirmed that the impact altered Dimorphos's orbit around Didymos by 32 minutes, so shortening the 11-hour and 55-minute orbit to 11 hours and 23 minutes. And they have a margin of uncertainty of about plus or minus 2 minutes, so quite confident in that. They're still continuing observations and continuing to do the modeling of the impact itself. Why was it 32 minutes? You have the mass of the spacecraft, but you also had that plume of material that came off of Dimorphos that also helped to give it that kick. And so trying to understand and model the physics of all of that. So they're having a ball with that. It's still ongoing, but to have the confidence to be able to come out there and say, yes, you know, success in this area, the orbit was changed and by this much. And here's some of the data that came down in these light curve measurements. Again, watching the light, you know, go up and down and up, and there's where they would have expected that dip from these kind of these eclipses, these transits to be, if the orbit had not been changed at all. But then there were dips appearing not in that location but elsewhere, and with a few different techniques, with different telescopes doing this, and then also comparing to planetary radar, you had some different checks on each other confirming this new 11-hour and 23-minute orbit. So this was a really valuable test just to try this technique, to get data on it, to be able to better understand it if this were ever to be needed one day, if it was needed to be scaled up and used on an asteroid. But it all depends on the asteroid and on its orbit, on its size, and really on the lead time. So everything always goes back to finding them early, But now we actually have a tool in the toolbox that's actually been tested. We'll have a better understanding of it and how it works on a real asteroid, which gives us a lot more confidence if we ever need to do this one day. And so kind of bottom line is, don't let this happen in your backyard. Support your local planetary defense office. But if you want more information on NASA's planetary defense activities, nasa.gov/planetary defense. We're also on NASA Asteroid Watch on Twitter. And so those are ways to find out more about the activities at NASA. And at this point, I am going to stop sharing, and I would be happy to take any questions. That's kind of the planetary defense fire hose, but thank you so much for your attention, and I'd be happy to take any questions. Thanks, Jeff.
Well, thank you. Thank you very much. That was fascinating. It's one of those science fiction scenarios until it's not. I'm wondering, yeah, we do have some, Gary, would you like to ask your question?
Thanks a lot for a fascinating presentation and good shooting. Way to go. Now, the first thing that comes to mind, I'm a bit embarrassed about this, but do you actually, let me turn this thing on. When you're designing the spacecraft, you actually make it more massive or anything like that. So it like, tell me a little bit about the spacecraft itself.
Well, it's about the size of a vending machine, the team says. But again, this was, this was just a test. And the nice thing is with this binary asteroid system, it's a lot easier and quicker to detect the change in motion of this one asteroid around the other than if this had been done as a test on an asteroid that was in orbit around the sun. So it was a way to kind of have this self-contained test. And so it wasn't a supermassive spacecraft. Our planetary defense officer likes to say it was small, but it was mighty. But this was for this, it was designed for this test situation because yes, if there was an asteroid that had to be deflected in space of that size, off of the Earth, avoiding some future impact, it probably would have had to be larger. So larger mass, but it's also it's the energy, and so the momentum, and so it's also the mass and the velocity, and so that's why like sometimes people say, oh, we got to have a mission ready to go on the launch pad if something ever comes up. Well, no, I mean, for a number of reasons, that's really not worth it because might not ever need it in our lifetimes. Technology's changing, then you got to pay to keep it up and everything. But it's because it depends on the asteroid. Like you said, it might have to be more massive, or maybe you'd use a series of kinetic impactors, or maybe, depending on the lead time, depending on the size of the object, you might use one of those other techniques that I mentioned. So that's kind of a long answer to say, yeah, you might need something. If it was a kinetic impactor, you might need something more massive. You probably would, but it also depends on the relative velocity that it would impact the object if it was faster than like the situation with darts. So there are a number of factors there. So this was just one case.
Good, thank you.
Thanks, David Lee. Do you want to ask your question?
Yes. Thank you very much, Kelly, for that great explanation. When you mentioned that the object that you targeted was relatively small and innocuous, how difficult is it going to be for you to scale up your results for something much more massive?
Well, certainly larger objects will be easier to autonomously target. So that's kind of encouraging. Just the fact that this all worked well, I mean, it has its heritage in other research, but I think that was really encouraging there that targeting worked, and it is all physics, and there are these teams like at the Jet Propulsion Laboratory and elsewhere that are really expert in doing orbital dynamics, and this is kind of used all the time for sending spacecraft science missions to planetary targets. And so at least that sort of technology to be able to get, use solar system dynamics to get yourself from point A to point B that seems pretty well in hand, and we saw a really good demonstration of the autonomous navigation capability. So that's all really encouraging that's all working. But it's true, if it is a more massive asteroid, you're going to need or even for this asteroid, again, this was a test of deflection in the orbit around another asteroid in space. It would take something bigger to deflect it if it were on an impact trajectory with Earth, and it would take. Otherwise, it would take a lot more lead time. You might need a couple of decades, but again, you'd design it for the asteroid in the situation that it's in. So it might involve scaling it up, more massive, or again, like multiple kinetic impactors, or just using another technique. So if it gets too large, you might have to use something like a nuclear device, which brings up many other issues, trying to, because there are all kinds of legal issues with that. And that's why some of these groups like the Space Mission Planning Advisory Group, that international collaboration, are looking at some of these issues as they have meetings, because again, you wouldn't want the first time you ever thought about it to happen in an asteroid threat situation. And so that's why this research is going on now, and might never even need to worry about it, but it's good to talk about it before it becomes a situation.
And again, once again, congratulations. Thank you.
Thank you. And I'm not actually on the DART team, so I'm there cheering them on too. So, but a lot of the observers in the program I run are involved in doing the ground-based observations. And so, and in fact, one of the follow-up telescopes that I displayed on that chart, Spacewatch, they actually discovered Didymos back in, I think it was 1996. So a lot of key players here.
Kelly, is that the same group out of Kitt Peak?
Yes.
Spacewatch?
Yes,
it is the same one, eh? Okay.
Yes.
Go.
So that's fabulous. Yeah.
Yeah.
Lauri, do you want to ask your question? Lauri DeRoche.
Sure. Hi. Thank you, Kelly. That was really fascinating. I wondered whether or not you had just in one slide that you said that you wanted to make a change in greater than or less than a 73-second change. Was it a greater than 73 seconds? Is that what the hypothesis was, that you wanted to make that change?
It ended up much greater. Yes. I mean, the team had, in coming up with the requirements for the mission, it needed to be, there needed to be confidence that it would be something that would at least be a change that could be observable from the Earth. And so, and they were very confident, just based on the physics, the mass of the spacecraft and everything, and the what could be inferred about Dimorphos, since it wasn't seen close up until right before impact. But there was enough known about it that they were confident that they could get a deflection of some amount. But it ended up being towards the higher end, being up at 32 minutes, which again I think it did. But they're working out the details on that, had to do with that combination of both the impact of the spacecraft, but then that plume of material coming off, giving that enhancement to the change in the velocity. So yeah, that was, they just had to get that level of, they had to have some idea of how much they had to deflect it just to be able to detect it from the Earth with confidence. But they did have their hopes set higher, and they were not disappointed.
Does it mean does it mean that then the little moon is actually going faster than around than it did before?
Right, or the orbital period is shorter, so it actually it slowed it down to have a shorter orbital period, because I know, it's kind of it actually, the spacecraft got in the way of the asteroid, so it slowed it down just a little bit, which dropped it into a little closer orbit, but that meant that the period then is shorter. So yeah, we slowed it down to have it go faster in a way, but it was slowed it down to have a shorter period, so it finishes its orbit quicker now.
And that was the original thing that they wanted to do. Like, they didn't want to make it go go the other direction. They always wanted it to go that way, right?
Right. Yeah, that was the intention with
Okay.
the ground-based observations. You know, they did a lot of those light curve measurements before the impact too, so they really so that they knew where to expect that Dimorphos, the smaller asteroid, would be, which side of Didymos it would be on, so that they could get in front of it to do that.
Okay.
It is kind of easier to get away and get smacked, get in front and get smacked by an asteroid than to try to come up and smack it. It's just you can just get a lot more oomph out of it that way by letting the asteroid smack you.
Okay. Thank you very much.
Anita Carpenter, do you want to ask your question?
Sure, thank you. My question is about the planetary radar. It's fascinating that we can bounce, radar off of these objects from Earth. And so how close to the Earth does it have to be able to do that? And the loss of Arecibo, is that a big impact, or is all the capability now at Goldstone to do that?
Right, good question. Because yeah, all of in terms of like NASA's capability for planetary radar, and really the most capable planetary radar that's available right now is the Goldstone radar in California. But Arecibo, that was a National Science Foundation facility that that NASA had put a radar on that radio telescope, and so that was a loss because it was a more powerful radar. And so with Arecibo, you could detect objects further away than you could with Goldstone. But we still have a lot of capability with the Goldstone radar, and I'm trying to. I don't have the question about the distances. I don't have it off the top of my head. I should have these. I think it's about like for Goldstone. Well, I think in general, I mean, it also depends. It depends on the size of the asteroid, but I think you could go out about a quarter of an astronomical unit, about a quarter of an AU, to be able to detect subjects. I think maybe closer, maybe a little closer if I'm remembering right with Goldstone, but it depends on the size of the asteroid. And also, radar is also used to study the surfaces of the moon and even Mars and Mercury and even out to the Galilean satellites of Jupiter. And Arecibo was used even for Saturn's moon Titan. And so Arecibo wasn't steerable, but it was a little more powerful. Goldstone is a steerable dish and still very capable, and also used with the radio telescope in Green Bank in West Virginia to do receive, which they also used to do with Arecibo, where you have this bistatic radar where one of them would transmit and the other would receive. Which was done for various reasons, and that was done for DART also. There was a mix of those observations. So, still making use of the existing capabilities, and so we're still in good shape, but still want to look to the future because even Arecibo was all very old radar technology, and so even though the National Science Foundation isn't currently moving ahead with rebuilding that telescope, even if something were to happen in the future there or elsewhere with the new capability, you'd want to use the updated technologies. So NASA does want to work with other agencies if it comes to that point to develop the capabilities that maybe could be utilized to have a more modern radar facility. But at the moment, it is the Goldstone radar, and it is providing what we need. But we're also smarting from the loss of Arecibo because that was a very useful radar for the community as well.
Thank you.
Thank you. Brock, do you want to ask your question?
Sure. Yeah, it was amazing to watch. But one thing that really stood out to me was the fact that it's just basically a big agglomeration of gravel. And then it made me wonder, does the fact, I always grew up thinking asteroids are just big rocks, but seeing it just being this big pile of gravel made me wonder if does that affect the strategies on dealing with it in space, and does it do we understand how that affects also an impact, the way it would break up in the atmosphere, or the kind of damage it would do?
Right. Yeah, we actually have a team out at NASA Ames in California that does modeling of asteroid entry into the atmosphere and impact, and what the structure of an asteroid, how that might affect, traveling through the atmosphere and reaching the surface of the Earth. But a lot of small bodies in the solar system are probably these rubble piles we're finding. I mean, if you've seen images of Bennu from OSIRIS-REx, or had the Hayabusa 2 target, Ryugu, they were just big rubble piles. And so that was kind of expected for Didymos, that it was, because it was kind of in that size regime, and from its shape from planetary radar before the impact, that it was thought, oh, that's probably a rubble pile. I kind of thought that, uninformed, that Dimorphos might be more of a monolithic type object. We've seen some objects like that. They kept using Itokawa as a sort of a stand-in for Dimorphos in some of the pictures and everything. But then, as the impact was underway and we saw it getting bigger and bigger, like, wow, it is a rubble pile. And so not all asteroids are like that, but again, we're still studying them, still learning how much of the population is like that. And like you said, it would be important to take into account in doing like a mitigation, doing a deflection, because you wouldn't want to just, you wouldn't want to totally disrupt it, because then you'd have all this material together heading for Earth. You'd really want to deflect it. And so you wouldn't want an impactor that would hit it too hard to disrupt it. And so that's something, again, that's why it was good to do a test here, and it's still there. So we didn't take it out, even though it ended up being a rubble pile. And that plume is actually valuable in terms of its ability to, again, give a kick to the rest of the larger part of the mass. But it's an important consideration. That's why, again, doing the survey of asteroids and getting them all cataloged, or at least get the bulk of them cataloged, is important, because if one does pose a threat, if you had years or decades of notice, you could send a characterization mission out there. You could send essentially a science mission out there to study the asteroid. And instead of seeing it for the first time, a few seconds before your mitigation mission, you could actually go out there, study it, and plan a mission that's targeted toward that particular asteroid and toward that situation. So it's a long answer to that. Yeah, with a rubble pile, you'd want to be careful.
Thank you.
Kelly, I just wanted to pause for a second, just so everybody knows, Kelly's speaking from the Eastern time zone. We're about an hour now into your talk. Are you okay to go on with some further questions?
Oh yeah, we can go on. I'm all in right now. Sorry.
Okay, Reg, do you want to go forward? Go ahead.
Yes, thanks so much for a wonderful presentation, Kelly, and congratulations on getting a bullseye hit on the target. I was curious to know if the DART trajectory was within the plane of the dimorphous Didymos plane, the orbital plane, or was it giving it kind of a glancing blow?
Do you mean, was the Didymos dimorphos plane kind of in the plane of the solar system? Is that what you meant?
No, I mean that when DART was coming in, was it when Dimorphos was moving around Didymos, was the DART going directly towards it, or was it coming up from below or from above in the Didymos Dimorphos orbital plane?
Right, it was pretty much going right towards it, or getting in the way of it. Again, the team had enough information from the ground-based observations to kind of know where it was going to be, what swing of the orbit it was going to be in as the spacecraft approached, and so they were able to line it up very well. But yeah, it pretty much hit it head on, which was the plan. The team is still kind of determining. I mean, I think they feel like it was maybe within a few meters of whatever the center happened to be. But yeah, it pretty much was head on. Everything was lined up. It was nice that, again, this system was that's what I was thinking in the plane of the solar system, because it might have been maybe a little more tedious if it had been tilted over. I guess maybe not that much, but it just it just worked out really well for this situation.
Well, congrats on an amazing accomplishment there.
Thank you.
Josh, do you want to go ahead with your question?
Were to like come and hit Earth, if we were to use a spacecraft to like deflect it, would it be like will we hit it like straight on, or like from the side of it, or like where would we move it to?
Right. It's probably easiest to like get in the way of an object, an asteroid or comet, and let it hit the spacecraft. It's kind of harder with the to get the energy if you were kind of coming up behind an object and hitting it. But it really depended. It would really depend on the situation, because you have the Earth going around the sun, and then you've got the asteroids going around the sun, and so as the Earth is going around the sun, to try to launch that spacecraft from there and send it to this object that's also going around the sun, all the motions have to work out. And so so it kind of depends. It depends on how the deflection would need to happen, and that's why studying it well ahead of time would be important, to be able to plan to hit it in the right way. But generally, the easiest thing is to would be trying to slow an asteroid down rather than to try to speed it up, because it is easier to get out there and put something in the way rather than to get behind it and try to give it a push from to make it go faster, if that makes sense.
Yeah.
But that's part of why, doing this test, because again, we can do all kinds of modeling and calculations, but to actually have a real test situation, now we've got some data to work with, and so that should help inform, in the future how this might happen.
Kathy or Dennis, do you want to ask your question?
Yeah. Yeah. Hi. So the whole thing is amazing. That watching this, and so question I have for you, Kelly, is now that this looks like it's been reasonably successful, or maybe very successful, is there a next phase? Is there a DART 2 project in the work? Is there thoughts of, okay, so now that we've accomplished this, do we need to look at another project, a bigger asteroid, different asteroid, something like that? Just kind of generally wondering, is there a next phase to this? This DART 2 looks like it's been quite successful.
Right. Certainly the science community would love to do that. But actually in the near term, in terms of the priorities, again, it gets back to, finding the asteroids, and we really need to speed up the discovery rate. And that's why, in terms of the missions, the Near Earth Object Surveyor Space Telescope is kind of the next thing in the queue. And after that, we actually, in the US, we just had this study. Every 10 years, there's this assessment by the National Academies of Science, Engineering, and Medicine, looking at the state of planetary science and what should the priorities be over the next 10 years, our decadal survey. And we just had that, and planetary defense was included in it. And so that involved all these peer review panels looking at, what should NASA be doing the next 10 years. And so they came back and confirmed that, yes, you've done DART, you've got to do NEO Surveyor next, you've got to find the asteroids. And their other priority for science mission is a rapid response characterization mission, something, whenever we have a mission to an object in the solar system, it does take years to design it, to build it, to do all the testing and everything, to launch it. Then there's the cruise to get it actually out to the object. And so to try to come up with a way to shorten that turnaround process, where if we, again, found a threatening asteroid, we wanted to get out there and find out more about it to be able to quickly launch a mission to go study an asteroid, and so that's something that the decadal survey said should really be the next mission priority. And so that's a very strong guide for NASA, these decadal surveys. So all of that is to say that no, there's no DART 2 in the queue yet, and there's DART 1 right now that's still underway. And so then, so further down the road, I mean, certainly the modeling is still going to go on with how what we learned from DART and how that could be applied to maybe other situations. But we'll have to see further down the road after we take care of these other shorter term priorities. It might be that maybe rather than the kinetic impactor technique, maybe we need a gravity tractor demonstration mission. So we'll have to see. So nothing in the queue at the moment in the US, and I'm not aware. I think maybe China said that they were thinking of trying to do a deflection mission also. I'm trying to remember now. But we'll have to see. But again, kind of now that we've done this planetary defense demo, it's still, getting back to basics, got to find the asteroids. So it's going to be the near Earth object surveyors, the next priority and characterization. But eventually it would make sense to try this again after we've kind of rolled up what we've learned from DART.
Great, thanks, Kelly.
Stefan Bedingfield, do you want to ask your question?
Yes, thank you. Wonderful presentation, Kelly. I really enjoyed it. Thank you very much. So I had a question. I think earlier in your presentation, you mentioned some collaboration both with NASA and the European Space Agency and that. And then you spoke later about this table test, which seemed to be more US centered plan on what do we do if we had essentially an incoming NEO. So I wonder, what does this look like globally? Have there been similar coordination exercises that you know of? And secondly, with your initial work so far in all aspects of the Center of the NEO studies, any other agencies there, from the initial work, what can we learn that would encourage global cooperation and collaboration, like in terms of needs, shortcomings, and strengths, etc.?
Right. Well, the question about kind of this, are there exercises that are done, on, not just a national level? Actually, there have been for a number of years. There is a international planetary defense conference that takes place every 2 years. And when we've had that conference, there has been a tabletop exercise associated with the conference. And so either playing out during the conference, or I think with this next planetary defense conference that's going to take place next year, the scenario is going to be all laid out, and then participants can submit papers that are related to that scenario. But these exercises have been done on an international level, just with kind of the science community, not with pulling in other agencies of other governments. Although this next planetary defense conference next year is going to be hosted by the UN in Vienna, Austria, and at the Office of Outer Space Affairs there. And so they're hoping to pull in some other participation, not just from the scientists from other countries, but from the government levels too, just to kind of get everybody thinking about what are the possibilities here. Also on the international front, we've done not these full up end-to-end type exercises, but with like the International Asteroid Warning Network, this collaboration of the astronomers, we've done exercises. In fact, we were just talking about the next one today, because again, the meeting just happens to be going on this week, where they've done exercises trying to coordinate on recovering, because again, we're going around the sun, the asteroids are going around the sun, we don't see them all the time. And so we did an exercise on recovering an asteroid that was a known asteroid, but the orbit wasn't known quite well enough. And so to try to recover it, treating it as if it was going to be a threat. And so to try to coordinate on recovering that asteroid. There was another exercise coordinating on trying to characterize an asteroid, get its physical properties to try to understand it better to the extent that could be done with ground-based telescopes. And more recently, the campaign involved, we called it a timing campaign because in this case, the target was a very well-known asteroid, and the participants, the different observatories, measured position of this asteroid and reported it to the Minor Planet Center. And then the data were analyzed to kind of see if there were timing errors, and there tended to be a bias in the observations, and it could have to do with like the time that was being reported. Are you reporting the middle of your observation, or is it when your shutter opens, or is it when your shutter closes? And so trying to kind of do some of these exercises to shake out some of the bugs in the worldwide system, just to make at least on the observing side, just to make it all the more excellent. So these collaborations are happening, maybe in focused areas on smaller scales. And then there's like on the mission side with the Space Missions Planning Advisory Group. You asked about, maybe what are some of the hindrances? I mean, it's just, dealing with bureaucracies and coordination and distance. And I mean, there's all kinds of things to slow things down, but that's why, how do you eat an elephant one bite at a time? I mean, trying to do things little by little, like working, just with the astronomers there, and we're kind of collaborating on how can we make things better in this area. In the tabletop exercises in the US, they started small. This year, that was the biggest one we'd ever had, pulling in other agencies. And now, thanks to DART, I think there's a lot of interest. And so that'll probably help all the more if people want to kind of get in on the action. And so that'll be good. Maybe that will open doors. So, but the exercises at the Planetary Defense Conference, those have probably been the ones that at least have gotten the broadest participation, but again, more from the people already in the field. And so we're hoping to kind of get more to other agencies and governments, just again, to kind of raise the awareness. And so that, and to start putting like some of those communications channels in place. I always say, if a threatening asteroid is ever discovered, it's going to be all over Twitter before NASA or any agency has a chance to say anything about it, because the data are all public. I mean, as it should be. People can pull the data and do orbit determination and all that. The data are all out there. And so at least speaking on NASA's side, NASA's goal is to, we don't have to be first with the information, but to be out there with, the correct interpretation of the information and the additional information, what we bring from all our researchers and everything. So, so there's communication, like what you're going to see, on social media, but then there's communication actually getting the information out there, like we did with DART this week, or this past week, holding a briefing as soon as the team was ready, had enough confidence in the numbers. Instead of waiting till the end of October, they got out there and released the information right away. I'm sorry, Jeff, I keep doing answers that are far too long. Sorry about that.
They're very, very complete answers. I think though, in the interest of time, we have one question online and then 5 questions queued up, and I think we'll stop at that point. Okay, so Tom has asked a question online, and I'll read it for everybody, although it's on the chat line. Kelly, you mentioned the gravity tractor approach, deflecting an asteroid. Changing Dimorphos orbit has in effect tested that technique too. So has a change yet been determined for the main body now that Dimorphos has been moved closer to it, and thus changed the center of gravity for the whole system?
Right, it's at least in terms of the gravity tractor technique, we would say really that, I don't know that we would call this a test of that, because it's more using gravity of one object to kind of tug on another object. But in this case, we really have not changed the center of gravity, because the bulk of the mass was really in Didymos, and Dimorphos hasn't gotten that much closer to it. And certainly, the change, even this change has not changed, appreciably the orbit of the Didymos system around the sun. So we wouldn't call this necessarily a gravity tractor test. And so yes, it has changed the center of gravity, but not to appreciable amount that it would change the orbit around the sun. So, which came up a lot, before impact. Is that going to change the orbit of Didymos, and could it put it in a situation where it could be a threat to Earth? But no, couldn't do that. This was small enough that really the change was just to Dimorphos and its orbit, and not enough to tweak everything else.
Thanks. I've just got a note from IT that this is going to stop at 9 o'clock. So we'll answer the questions we can, but my apologies to anybody whose questions we haven't been able to ask. I'm going to have 1 minute. I'm going to leave 1 minute for remarks. So Layla, do you want to ask your question?
Hi, yeah, thank you for your presentation. My Wi-Fi did cut out at one point, so I may have missed this info, but what made the DART team choose this specific deflection method as opposed to, let's say, sending an object next to the asteroid or its moon to affect it gravitationally, and what factors may determine this decision for future deflection missions?
Well, again, the kinetic impactor is kind of the simplest deflection technique, so it made sense to, and it's kind of the most simplest, most mature, so it made sense to test that at first. And it was originally supposed to be kind of a coordinated mission with the European Space Agency, or two coordinated missions where there would be a spacecraft there at the system, because again, you had this binary asteroid system coming close enough to Earth to observe from the Earth. So it was a good opportunity. So it's just nature gave the right situation that was kind of customized for a kinetic impact, and because it just helped to have this binary asteroid. But the European mission wasn't funded in time to be there, but a modified version of it is called Hera, and that is actually in development and will launch to go study now what really to understand and study the Didymos system in detail, look at the crater that was formed by DART on Dimorphos, study the properties of the asteroid, try to understand more about its composition and everything. And so that'll kind of further help characterize the system. So all that is to say that originally there were going to be two missions. And so it was just nature giving us this opportunity at this time, because we don't always have a binary asteroid flying by at a certain time to be able to do ground-based measurements so it was just a mature technique and a good opportunity.
Awesome, thank you.
Chris, do you want to try to get your question in there?
Yes. So today I was, by coincidence, I was reminded that there, at one time, people were looking at changing the reflective properties of asteroids and things to change their orbital path, perhaps by applying some foil or even paint. And I wondered if there was where that's all gone.
Right, just real quick, asteroids absorb sunlight and re-radiate it, and actually and they're spinning, and so that absorption and re-radiation can actually give like a little push to an asteroid. I mean, very small, but that's something that the OSIRIS-REx mission studied when it was at Bennu. It's called the Yarkovsky effect, and so there are these other physics that happens because of the heating by the sun, re-radiating. And so if you were to change the surface color of an asteroid, you could maybe control that some and maybe give some oomph to that. And so that's another area with people have said maybe you could deflect an asteroid, again, if you had lots of time by changing its surface coloring, and then that kind of absorption and re-radiation of heat, and that could affect its motion.
Okay, thank you. David, do you want to try to get your question in there?
Sure, I'll try and be quick. Imagine the question: if you spot an asteroid, you have to know its trajectory very, very precisely to give an answer, yes or no, it's going to impact the Earth. So you're dealing with probabilities, and you can take different approaches. You can say, I want to get rid of anything that comes anywhere near, or are you looking for a binary answer? And that's going to reduce the amount of time you have. And I just want to sense, is someone looking at all these probabilities? Then there's a danger, well, maybe the right answer is to do nothing.
Well, Ryan, hopefully, you know, that is the right answer with everything out there. You know, if we don't need to do anything, it's that's the good answer. The Center for Near Earth Object Studies that I mentioned, you know, they take all the orbits of all the known objects and calculate them in the future and see if anything could pose an impact hazard. And they and also our European counterparts, you know, maintain a list. It's on their website. They use this. It's on the Sentry page. They use the Sentry system. But all of those probabilities are down like at, you know, 10 to the -4, 10 to the -6, you know, these very low probabilities that an impact could happen. That with the International Asteroid Warning Network and the Space Mission Planning Advisory Group, you know, when something hits, you know, something that could pose, you know, something larger that wouldn't just be a pretty fireball, hits the 1% level, that's when they start paying attention. But it's true that you're dealing with probabilities. That still means 99% it's not going to hit, but you want to start paying attention. You want to get more information to narrow things down so you know for sure, as you saw with that 2022 EB5, that impact that happened earlier this year. You know, there was kind of that uncertainty, you know, it was going to hit the Earth. Sometimes you have it where those probabilities go way off the Earth, or the possible impact locations are way off the Earth. There it was on the Earth, but it took a while to get enough information to narrow it all the way down. So that's the thing is in a whole impact scenario, it could be that certain period of time, you only have enough information that you know that, you know, maybe this broad swath of the Earth could be possibly affected, but ultimately there's only going to be one spot, but figuring out where that spot is. And so it takes more and more information to narrow that down. So yeah, good question about that, because they are dealing with probabilities. And the nice thing is right now, there are no probabilities that are up at the level where we start saying, okay, we got to really buckle down here. So that's a good thing.
That's good. Yeah. Thank you. Great talk.
Victor, you know, I'm sorry about this, but we're really at the end and we just need a couple of minutes. If you want to post your question, though, I will send it to Dr. Fast and see if we can get an answer for you. Kelly, thanks for a very interesting and stimulating presentation. We all wish you continued success in living up to your tagline, find the asteroids before they find us. One of the drawbacks that's occurred with Zoom is an inability for an audience to clap, showing individual appreciation. There's lots of thank yous coming in online, but on all of our behalf, I'd really like to thank you for speaking to us this evening.
Thank you so much for the invitation and the great questions. I really appreciate it. This is a lot of fun.
Take care. For any of the other members here still, I guess we will move into the meeting. Lauri, did you want to try to I'm not sure if we end suddenly at 9 or what happens.
I just wanted to say to anybody of the members that if anybody wants a calendar or any of the other workbooks or anything that we are going to order, please just email me and I can get that. Chris Purse has already sent things out. Please just email me and let me know. We've still got some to go. And that's all I really wanted to say was just we're putting in the order pretty soon. So if you would like one, just call me or email me. Thanks all. Thanks.
Thanks, Lauri. And David has deferred his comments to the next meeting. So that really ends the meeting. Thanks everybody for joining us. Bye-bye.
Good night.
And thanks, Jeff, for hosting us this evening. That was great.
Not a problem. It was fun. Take care. Good night.
All right. Bye-bye.